Today, I am pleased to introduce Dr. Wei Zhang. He is a postdoctoral research fellow, or excuse me, a postdoctoral research associate at the Princeton University Atmospheric Oceanic Sciences, the AOS program, as well as the NOAA Geophysical Fluids Dynamics Lab, GFDL. He holds a bachelor's in ocean science from Nanjing University in China and a PhD in meteorology and physical oceanography from the University of Miami. His research expertise right now in climate dynamics and prediction, the air-sea interaction, and high-resolution modeling. And a couple of his current research projects, which I both think are extremely interesting, using statistical and dynamic models to understand the climate variability and predictability over subseasonal and decadal timescales, particularly pertinent to our PPAI panel at CLIBAR, as well as developing deep learning methods to improve ENSO prediction. And that's funded by the Microsoft AI for Earth grant that you probably have heard about as well. So I will introduce this title. The title of today's talk, The Signal-to-Noise Paradox in Climate Models. If you're not sure what the signal-to-noise paradox is, I'm sure you'll hear about it here. And then Wei, I'll go ahead and pass it off to you to introduce your talk. Thank you.
All right, thank you, John. Thanks for your introduction. And hello, everyone. Thanks for coming today. I'm so glad to talk about my recent research on the signal-to-noise paradox in climate models. This study is done in collaboration with Dr. Ben Coltman, Dr. Amy Clement, Dr. Liz Quitter from University of Miami, and Dr. Baoqiang Xiang, Dr. Tom Dowers from GFDL, and Dr. Jeher from Georgia Tech, and others. You may also get in touch with me through my email address and personal website. All right, let's talk about this exciting and new topic in climate prediction, the signal-to-noise paradox. So the first question you may ask is, what is the signal-to-noise paradox? So let's look at this figure first. This figure is from Smith et al. 2019, showing example of the signal-to-noise paradox based on the decadal hindcast of the NAO. The y-axis is the correlation scale, and the x-axis is ensemble size. The blue curve indicates the correlation between the model ensemble mean forecast and individual ensemble member forecast. And red curve corresponds to the correlation between the model ensemble mean forecast and the observation. So in the ensemble-based climate prediction, model ensemble mean forecast generally shows higher correlation with observations than with individual ensemble member forecast. This may lead to a paradox that the models make better predictions for the real world than predicting themselves. In other words, the actual prediction scale is higher than the scale with a perfect model. The signal-to-noise paradox highlights potentially serious issue with climate models, as previous seasonal-to-decadal model-based predictability estimates may have been too low or underestimated. Understanding the signal-to-noise paradox may help identify the potential issues in the forecast system in order to provide guidance on future model development and initialization. This slide shows the outline for this presentation. In the first part, I'll focus on if we can reproduce a paradox behavior with a simple statistical model, such as the Markov model. Since the signal-to-noise paradox was first identified in the NAO index, we'll apply the Markov model to determine existence of the paradox in the NAO first. In part 3, we'll re-examine the decadal climate predictability in CMIP5 models from the perspective of the paradox, so that we can figure out if the paradox is related to the model predictability estimates. Possible solutions to eliminate the signal-to-noise paradox behavior particularly increasing ocean model resolution, will be discussed in the last part. So, part 1, can we reproduce the paradox behavior with a simple Markov model? Here we simply consider climate variability as a Markov process and introduce a Markov model framework to represent the ensemble forecast and to understand the signal-to-noise paradox. We first build up the observations and the free-running model based on the Markov model. And we simply assume that the forecast of the future state depend linearly on the current state and a stochastic error term, where alpha and beta here are -1 autocorrelation coefficient, indicating the persistence of the system. N and P are unpredictable white noise. Then we can make forecasts based on perfect initial condition, which is observation. The unique part of this Markov model framework is that we use observation as initial condition, while we keep the key parameters, say the beta and the P, from the free running model. And with different noise realizations, we can make ensemble forecast. And the ensemble mean forecast is given as follows. As suggested by Skip and Smith 2018, the ratio of square correlation can indicate the existence of the paradox. When the ratio of square correlation is greater than 1, there's a paradox. So we can mathematically derive the correlation between the model ensemble mean forecast and the observation, and the correlation between the model ensemble mean forecast and the individual ensemble member forecast. And we can do the ratio, right? So here we provide a very simple formula for the existence of the paradox based on the Markov model framework. That is, the paradox exists because the observed persistence and noise ratio is greater than the models. This plot shows an example of the paradox based on the Markov model framework. As you may see in Figure A, we give values to alpha, beta, sigma n, and sigma p that satisfy the formula we just derived. The y-axis is the ratio of the observed persistence to noise variance, and x-axis is the model persistence divided by model noise. Then we can make the plot of the corresponding correlation scale in Figure B. As you may see, the red curve indicates the correlation between the model ensemble mean forecast and the observation, and the blue curve is the correlation between the model ensemble mean forecast and the individual ensemble member forecast. We can see that the model ensemble mean forecast is higher correlated with observations than with individual ensemble members. So we successfully reproduced the signal-to-noise paradox based on the Markov model framework. And we further argue that the existence of the paradox depends on the relative amplitude of the persistence noise ratio between the models and observations. In other words, the paradox occurs because the models are less persistent and containing too much noise. The following question is, if we can use a Markov model framework by estimating the persistence and noise ratio to determine the existence of paradox in the NL index, as suggested in earlier studies. As I mentioned in the earlier slide, the signal-to-noise paradox was first identified in the seasonal prediction of the NL. So this bottom plot shows the variations of the monthly NL based on the observation and CMIP5 model historical simulations. These noisy gray curves are model simulations, and the black, red, yellow, and blue curves indicate observational estimates. The observed monthly NL indexes show generally consistent variations and highly correlated, as we may see in this figure. And different observational datasets ensure that we thoroughly consider the observed uncertainty in monthly NL index from different sources or based on different NAO methods. This table shows climate models from CMIP5 and CMIP6 project. We mainly use historical simulations with changing external forcing consistent with observations, and the PI control and the MU simulation are also used in this study. We have a total of 55 models used in this study. Okay, so to determine the existence of the paradox in the NL index, we first evaluate 4 parameters alpha, beta, sigma n, and sigma p in observations and study CMIP5 models. As suggested by the Markov Model Framework, the ratio of persistence and noise variance can indicate the existence of the paradox. Figure A shows autocorrelation function for the observed and model-simulated monthly NL index. This thick black curve accounts for the observation, and these cutout lines are CMIP5 models. As we may see in Figure A, at lag 1 month, the observation shows longer persistence than most of CMIP5 models. So from Figure A, we can derive the parameters alpha and beta, the persistent parameters for the observation and the model, respectively. Figure B shows the noise variance estimated based on the Markov Model Framework. The black dot here is the observational estimate, and these color line dots are CMIP5 model simulations. You may see that most CMIP5 models have larger noise variance than the observation. Figures C and D can indicate the existence of the signal-to-noise paradox. The y-axis of Figure C is the persistence noise ratio for the observation, and the x-axis is for the models. So most CMIP5 models have smaller values of the persistent noise ratio compared to the observations, indicating the existence of the paradox. This is much clearer in Figure D, showing the ratio of square correlation. As you may recall, the ratio of square correlation, when the ratio of square correlation is greater than 1, there's a paradox. And results suggest that over 80% of CMIP5 models have a signal-to-noise paradox for the monthly NL index, suggesting the widespread existence of the paradox in CMIP5 models. And more importantly, the paradox applies to the CMIP5 uninitialized historical simulations, implying that the paradox is not due to the issues in the initialization processes, but instead is a general model problem. So, in addition to the all-year monthly NL index, people are more curious about winter NL that has larger effect on regional climate. This plot shows the DJFM winter NL index from 1870 to 2005. The black, red, purple curves are observational estimates, and a bunch of gray curves are CMIP5 historical simulations. And again, different observational data with different methods of NAO are generally consistent. This panel shows autocorrelation functions for winter NO index and 10-year low-pass filtered winter NO index. The thick color lines account for observational estimates, and these gray lines indicate CMIP5 model of historical simulations. And again, you can see that in the autocorrelation plot, the observation is more persistent than most of the CMIP5 models in both the unfeatured and the featured plot. And consistent with monthly NOAA estimate, the persistence of winter NO is generally underestimated by CMIP5 models, and the ratio of square correlation, which is not shown here, but is generally greater than 1 in most CMIP5 models, indicating the widespread existence of the signal-to-noise paradox behavior at different timescales. The ratio of square correlation is further estimated for the global sea level pressure field during the winter seasons based on the 55 CMIP5 and CMIP6 models. So when the ratio of square correlation is greater than 1, this paradox, both AMIP and historical simulation show the existence of paradox in the North Atlantic region. This is a region where the NL index is calculated. It's very interesting that in the tropics, the AMIP simulation shows, the AMIP simulation based on the atmosphere only models seem to be less likely to have the paradox behavior than the historical simulations based on the couple model. A possible reason is that the AMIP simulation uses a prescribed SST, which is more persistent than the model simulated SST. Another interpretation may be related to the strong air-sea coupling in the tropics. So a recent study published in Nature by Smith et al. 2020 suggests that the North Atlantic climate is far more predictable over decadal timescales due to the paradox. And the results based on Smith et al. 2020 are based on the decadal hindcast of climate models. And differently, in this part, we estimate the decadal potential predictability in CMIP5 model historical simulations. This panel shows SST decadal predictability based on the observational data and CMIP5 model historical simulations. And decadal SST predictability is estimated as the ratio of 5-year low-pass filter variance to the total variance. So that's decadal potential predictability. Here we used 3 observational datasets, including the HEDI SST, COPY SST, and EISST version 5. And figure A shows the mean values of the decadal SST predictability based on these 3 observations. Figure B shows the mean values of decadal SST predictability based on CMIP5 models, in particular 30 CMIP5 historical simulations. So this kind of the multi-model mean estimates. And we only use the first realization of each CMIP5 models to equally weight each model in the multi-model mean estimates. It's clear that the observational estimates show longer decadal SST predictability than the models in most regions. And in figure C, we examine 6 different regions, including the North Atlantic, North Pacific, Eastern Tropical Pacific, Tropical Indian Ocean, Tropical Atlantic region, and Southern Ocean. The black dot indicates multi-model mean estimates, and the colored triangles are observational estimates. And we argue that the decadal SST predictability is generally underestimated in CMIP5 models in different ocean regions. This panel is similar to the last slide, but for the atmospheric variable sea level pressure. Figure A is the mean values of decadal SLP predictability based on 3 observational SLP data, and figure B is multi-model mean estimates of decadal SLP predictability based on 30 CMIP5 models. And again, the observational estimates show higher decadal predictability than CMIP5 models in most regions. And this underestimate is more significant than the decadal SST underestimates. And in figure C, the decadal SLP predictability based on the observations is greater than almost all the CMIP5 models in different ocean regions. So here we argue that the decadal predictability of stable pressure is substantially underestimated in CMIP5 models. Here we focus on the decadal SLT predictability and try to answer the question if this underestimate of decadal predictability is related to the signal-to-noise paradox. Figure A shows the difference of decadal SST predictability based on the observation and CMIP5 models. Figure B shows the occurrence probability for the signal-to-noise paradox at decadal timescales. The existence of the paradox is determined by the Markov Model Framework by estimating the persistence and noise ratio for each model. For example, in Figure B, the red color region, such as the eddy-rich regions, including the crucial current, Gulf Stream, Southern Ocean, as well as the tropical Indian Ocean and tropical Atlantic region. In these regions, it's very likely for the paradox to exist because over 90% of the CMIP5 models show the paradox behavior. This happen to be regions where models are underestimating decadal SST predictability, as you may see in Figure A. The pattern Figure B is somewhat consistent with Figure A, and we speculate that decadal predictability is likely to be underestimated in regions where it's likely to have a paradox behavior. And we also look that there's some inconsistency in the Eastern Tropical Pacific, which could be related to the acid coupling in the tropics. This figure shows the impact of external forcing on decadal predictability and the signal-to-noise paradox. As mentioned in earlier slide, the historical simulation is a simulation of past climate with increasing external forcing consistent with observations, and the pre-industrial control simulation is a simulation applied with constant external forcing at pre-industrial level. So Figure C shows the difference of decadal SST predictability based on CMIP5 historical and PI simulations. The difference of these two indicates the impact of external forcing on decadal SST predictability. You can see that the tropical Indian Ocean and tropical Atlantic region, as well as part of the North Atlantic region, are significantly impacted by the external forcing in terms of the decadal SST predictability. Higher decadal SST predictability is detected with historical simulations than the PI, accompanied by higher possibility of the existence of the paradox in the PI simulations, as you may see in Figure D. So, better simulated external forcing in a warming climate suggests less chance of the signal-to-noise paradox. This panel shows the ratio of square correlation for 30 CMIP5 models at 6 different ocean regions. The regional mean index was created to examine existence of paradox based on the Markov Model Framework. If the ratio of square correlation is greater than 1, there's a paradox. In regions such as the North Atlantic, tropical Atlantic, and Southern Ocean, it's very likely for the models to have the paradox behavior. And meanwhile, in regions like the North Pacific and Eastern Tropical Pacific, there are only half chance for the paradox to exist. So we conclude that the existence of the paradox varies with regions and models. So for this part, we argue that there's close relationship between the underestimate of decadal climate predictability and signal-to-noise paradox, despite of some uncertainty in regions like the Eastern Tropical Pacific. models tend to underestimate decadal predictability in regions where it's likely for the paradox to exist. All right. So in the next part, we're gonna diagnose possible solutions to eliminate the signal-to-noise paradox in climate models. One common issue in climate model, such as the couple models from CMIP5 and even CMIP6, is associated with the low ocean model resolutions. This so-called eddy-parameterized model can't resolve many mesoscale ocean processes. This figure is from Sequeira and Coatman 2016, comparing low resolution and high resolution model simulations in terms of the SST and subsurface ocean temperature anomalies in the North Atlantic region. The red box regions are the vertical structure of the subsurface ocean temperature anomalies in regions between these two black lines along the Gulf Stream extension region. Comparing these two plots, we find significant difference in terms of the SST and subsurface ocean vertical structure between the low resolution and high resolution model. And in the high resolution model, the red plot, we can see many small scale ocean processes happening in the subsurface ocean, which is totally missing in the low resolution model. As suggested by several previous studies, this difference in subsurface vertical structure may potentially affect decadal climate variability and predictability. So here we perform two experiments using CSSM4 with low resolution and high resolution model. This is a structure of a standard CSSM4, including the 4 component models of the ocean, sea ice, land, and atmosphere. And all of these component models are connected through a coupler in the middle. So for the low resolution experiment, the ocean and sea ice models resolution is 1 by 1 degree, and we've conducted a total of 500-year control simulations. And in the high resolution experiment, we use eddy-resolving ocean model with a spatial resolution of 0.1 degree by 0.1 degree, and we've run the model for 250 years in total. The atmospheric and net model resolution in both experiments are generally the same, so the only difference relies on the ocean model resolutions. Here we first compare decadal SST predictability between the low resolution and high resolution models. The left panel shows the ratio of high resolution and low resolution model decadal SST predictability. You can see that the high resolution model shows higher decadal SST predictability in many eddy-rich regions, such as the Gulf Stream, the coastal current, Southern Ocean, as well as the tropical Indian Ocean and the tropical Atlantic Ocean. And in the red panel, we first estimate the persistent noise ratio for the low resolution and high resolution simulations, respectively, based on the Markov Model Framework. And then we calculate the ratio of high resolution and low resolution model in terms of the persistence and noise ratio. So the red color regions indicate that the persistence and noise ratio in the high resolution is greater than the low resolution model, suggesting less chance for the paradox behavior in the high resolution model. Generally speaking, compared with low resolution model, high resolution models suggest less chance of existence for the paradox in regions where longer decadal predictability is identified, except the tropical Pacific region. And we further hypothesize that the strong vertical connectivity between the SST and subsurface ocean temperature may lead to the increased decadal SST predictability in the high resolution model. So in this slide, we show the correlation between the SST and subsurface ocean temperature averaged over the upper 500-meter depths in the net panel, and the correlation between the ocean heat content and net heat flux on the red panel. Both panels can indicate the difference of subsurface vertical connectivity between the low resolution and high resolution models. And the upper panel shows the results based on the high resolution simulation, and the bottom panel shows the result based on the low resolution simulation. Comparing low resolution and high resolution simulation, and we find that there's a stronger subsurface vertical connection in the black box regions, the eddy-rich regions, including the Gulf Stream, coastal current, and the Southern Ocean. In the high resolution than the low resolution simulation. These happen to be regions of increased decadal SST predictability in the high resolution models. This further supports our argument that the strong vertical connectivity in the eddy-resolved ocean model may contribute to the increased decadal SST predictability. SST is better connected with slower processes deep down in the high resolution model, making SST more persistent and predictable over decadal timescales. All right, just to summarize. So in part one, we use a Markov Model Framework to successfully reproduce a signal-to-noise paradox, and the paradox exists mainly due to the lack of persistence in models. And in part two, we find the widespread existence of paradox behavior in CMIP5 and 6 models based on the Markov Model Framework, which is consistent with earlier studies based on hindcast experiments. In part three, we argue that decadal climate predictability is generally underestimated in CMIP5 models, which we argue is due to the paradox. Decadal predictability is likely to be underestimated in regions where it's likely to have a paradox behavior. In the last part, we perform CSSM4 experiments comparing low resolution and high resolution simulations. We argue that the increased ocean model resolution may potentially or at least partially eliminate the paradox behavior, which is related to the increased vertical subsurface ocean connectivity in the high resolution model. And there are three major implications in this study. First, we developed a simple statistic framework to understand the signal-to-noise paradox, which may serve as an efficient tool to determine the reliability of the model simulations and prediction. Second, model-based decadal predictability estimate may have been too low, suggesting considerable room for improving climate model predictions over decadal timescales. Third, increasing ocean model resolutions can improve decadal climate prediction with more meso-scale feature results, which may be applied to future decadal prediction studies. So that's all for my talk, and thanks for your attention, and I'm ready to take questions. Thank you.
Thanks, Wei.
Thanks.
Great talk. I really enjoyed that. Thank you. And I'm going to ask you just a real quick question first before we take other questions. And if you do have questions, feel free to raise your hand. But my quick question was, when you stated before about in a warming environment or you kind of externally forced environment, and the idea was that the persistence or the paradox was actually less than in the pre-industrial force. Do you think that is because of in a warming or externally forced environment, you have a stronger signal and it's easier for the models to pick out that signal because you have a larger range and more variability, or is it something else?
I think,
yeah,
I haven't touched much about the external forcing. There's a paper by my friend Jeremy Cleverance. he published a paper early this year about the external forcing, how external forcing may impact the signal-to-noise paradox. I think from my own experience, because we have external forcing, so it's like you better simulate the climate signals that you mentioned as the real world. So it's like you generally mimic the real world, so you get less chance of existence for a paradox, since the paradox can can determine if these climate signals doing better or doing worse than the real world, right?
Looking forward to reading more about that. That kind of struck me first thing about I want to look into that.
Okay.
If you have raised your hand, please. I see a few hands raised. I'll go with Balu first. You can unmute yourself and ask your question if you like.
Okay. Hi, this is Balu Nadiga. Enjoyed the talk, but I have a question in connection with the paradox. In particular, while you seem to have focused on the shorter persistence in models, it's rather clear that the observational noise, estimation of the observational noise, I mean, the existence of this paradox can be quite sensitive to the estimate of noise in the observations. Can you say what you've done? I mean, what kind of uncertainty quantification have you done in your estimate of all of the results will be very sensitive to that. So what is can you talk a little bit about the procedure and whether you've done any uncertainty quantification in the estimate of observational noise?
So you mean the uncertainty of the observation, right?
Yeah.
That's a good question. So for the annual or SLP data, I just for the annual index, I applied many observational SLP data or the real analysis data to combine all this together to see if there are many uncertainty in the observation. And what I found is that, as you may see in this time series, I take this example to show the monthly annual index, and most of the observational estimates of annual show very consistent variations, and the persistence are generally the same.
Right.
So,
no, as I said, I mean, you were focusing more on persistence, but the question is one of estimating noise in the observational record, right? Because that appears in the denominator and is just as important.
So you mean how to estimate the noise for the observation?
Yeah, and in particular, the uncertainty that you have to associate with that estimate.
All right, so let's touch a little bit about the method of the Markov Model Framework that I applied here. Actually,
right. I mean, the main thing is with models, you have ensembles, and you have a much better chance of properly estimating P. Whereas with observations, you don't have that luxury. So the uncertainty in the estimate of N is likely to be much higher.
Yeah, I agree with you. The point is, actually, in the observation, we only have one simulation, right? But we apply this method just to, a very simple statistical method, just to give a rough estimate of the persistence and noise that can somewhat explain why the paradox exists.
No, I think that's very nice, right? Your Markov model is very nice. But when you apply it to NAO and things like that, that's where the issue is, when you're actually applying it to the observational record, real observational record. Okay, perhaps we can continue this offline.
Yeah, we can talk a little bit later, because I didn't quite get your question. Sorry. Yeah, we can talk about that later. Yeah.
Doug Smith, you can please unmute yourself and ask your question, and then we'll move to John.
Okay, can you hear me?
Yes.
Yes.
Great. Thanks for a very nice talk. Yeah. I particularly like the way that you're diagnosing, you're making a comparison between predictability estimates now and the signal to noise paradox. I particularly like that. But my question was, so you showed with the very high resolution ocean that there's more persistence in SST. Do you also see more persistence in atmospheric variables like sea level pressure in those experiments?
So you mean in the same simulation, or you mean another round of experiments about the atmospheric resolution?
So you're running coupled experiments as far as I can see, but you've changed the ocean resolution, and you're showing that the ocean becomes more persistent. But does that persistence also feed through into the atmosphere? Do you see more persistent NEO, for example, in those simulations with a very high resolution ocean?
Actually, I didn't pay attention to the NEO since, I don't know, since most of the atmospheric resolution remains the same. So my expectation is that there could not be much improvement from the ocean model resolution if you take a look at the atmospheric variable. But I think I'll take a look at it later.
I think that would be interesting to see, because the paradox is clearest, I think, in things like the NAO, and it's possible that the ocean atmosphere coupling, could be the cause of this paradox, and that when you increase the ocean resolution, you better resolve some of those coupling processes that could give more persistence in the atmosphere. So it'd be really interesting if you look at that and do find that. I'd be very interested to know that. But thanks for a nice talk.
Yeah. Thanks.
Okay, John, and then we'll go back to Balu.
Okay, thank you. Yeah, nice talk, and yeah, I like Doug's suggestion. I think there may be I had a couple of quick questions. I think first one is even in the Markov model, predictive skill improves with number of ensemble members, but I didn't see that there's any dependence of the paradox on the size of the ensemble. Is that correct?
Yeah.
Okay. See, that was quick. Second one, you showed that for the NAO predictability study you did, you showed different signal noise to persistence ratios for different models. Did you look to see whether the CMIP ensemble has different predictability with respect to predicting different ensemble members based on the ensemble members signal noise to persistence ratios?
So actually in each CMIP5 model, I just pick up just one realization to estimate the persistence and noise ratio. Since we assume that each model is equally weight, and since different models have different, some models have more ensemble members and some have fewer ensemble members. So we just pick one, since we can use this Markov Model Framework to determine the paradox based on one realization, such as the observation, right?
Yes, I understand that. But if you take your multi-model mean and try to withhold one of the models and try to predict that model with the multi-model mean, presumably you should be able to predict the multi-model mean of the more persistent models. You should be able to predict the more persistent model ensemble members more accurately than the less persistent ensemble members.
Yeah, that's a good point. Yeah,
that would also illustrate how important that aspect
Yeah.
of it is to other errors in the models, for example.
Yeah. Thanks.
Thank you.
Balu?
Okay, so this is with your fourth part where you talk of the increased vertical connectivity at high resolution ocean in a high resolution ocean.
Okay.
But by the same token, once you resolve this, there are two parts, two questions I have in this context. Once you increase the resolution in the ocean to be able to resolve the mesoscales, obviously you also expect an increase in the natural variability, right? I mean, so you didn't talk about that. The denominator, again,
Yes.
now in the model context. So that's one. And then the other one, and the other question is regards the parameterizations that are typically used in the low resolution models as far as the vertical connectivity is concerned. Why do you think a whole host of models seem to underestimate that connectivity? I mean, if you think of it from a process point of view.
Yeah, that's a good question. I answer the second question first. So I think you raised a good point to discuss here. Actually, there's still on debate if we increase the ocean model resolution can actually increase the vertical connectivity that contribute to the increased decadal predictability, or like better parameterization, like the vertical or horizontal, the layer of the ocean model that contribute to better decadal SST variability estimates. From my experience, I do find in our model experiment, we have like generally same layers of the low resolution, high resolution model, ocean model, and the key difference between the low resolution and high resolution is that if you look at the different layers of each of the ocean models, you can see very many mesoscale ocean processes, and the vertical connectivity of each layer kind of increased in the high resolution models. So
it's interesting,
like,
right? I mean,
yeah.
The picture of ocean dynamics is one of isopycnal mixing and the general outcropping of isopycnals, and you're talking about diapycnal mixing, right?
Yeah,
which is kind of a very small quantity, right? I mean, when you resolve the mesoscales. Okay.
Yeah.
But what about the first one? I mean,
could you pardon, please?
Yeah, the likelihood of an increase in natural variability when you increase the resolution of the ocean model. Right. So even though there may be increased persistence, as you see, there is also an increase in the natural variability. So the numerator and denominator are both increasing.
Yeah, that's also on debate, I think, since I don't know if I understand you correctly. You mean that when you increase the ocean model resolution, you increase the noise, right?
Yeah.
So is that what you mean?
Yeah.
So it's also a very debatable question. My point is, when you increase the ocean model resolution, you get a better simulation of the SST. So that's more consistent with the observations. So it's like you get better simulation of SST that contribute to better estimates of predictability. That's my point. And there's a debatable point that when you increase the ocean model resolution, in the meanwhile, we introduce the noise. So that could possibly reduce the predictability, right? But my point is the first one, yeah. So
no,
this
I mean,
question
like
is
your
beyond
first
debate.
part, Markov model shows
yeah,
it's the ratio.
Yeah.
All right.
Are there any other questions? Okay, without seeing any, Wei, I just want to thank you again for your talk. Thank you and answering the questions. And I will pass it back to Jenny.
Great, thank you, John. And thank you so much again, Wei, for your presentation. Again, to everyone, a recording of this talk will be available next week, so I'll send out a link once it's available. Our next PPAI webinar, I believe, will be in January. I think the panel members will take a break in December, as you know, they'll be busy with all the large conferences and prepping for the holidays. So join us on January 19th for a talk by Doug Smith, who is also on this call today. So we very much look forward to your talk, Doug. And again, thank you so much, Wei, and to you, John, for moderating this webinar. Have a great day, everyone.